Alright, the goal for today is to introduce two more tests that can be used to determine if various series converge or diverge. Very important because if you're even going to stand a chance at estimating the value of the series, you should really know that the series has a value in the first place. So we're going to have two tests today. We're going to have the direct comparison test, which I admit is not actually my favorite. I use direct comparison test fairly infrequently compared to the other test that we will be introducing today, limit comparison test, which I just, chef's kiss, love this test. It unlocks so many possibilities in terms of series whose convergence/divergence you can unambiguously determine. So let's state these tests, let's practice using them, and let's of course identify valid and invalid uses of these tests. Here's the setting, here's the motivation. We have so far covered the situation where we had series whose formulas could be integrated, but that's not the case in any one of these scenarios. Maybe some of them theoretically could be integrated, but actually integrating them would require so much work that it would be really pretty annoying. Maybe some of these are going to require a trig substitution, heaven forbid. None of these series work out to be telescoping, and they're also not geometric. The one at the bottom is partially geometric. It does have 1 over 2 to the k. However, it is not fully geometric because it also has the k in the denominator. So we cannot use that theorem for convergence of geometric series. Neither is any one of these series a p-series. So that theorem is out as well. Additionally, for all of these series, the divergence test is locked because the limit always goes to 0 for each of these sequences. And not only that, but we also cannot use the original definition of convergence because it's just too hard to find a formula for the nth partial sum. Now, the thing that we're going to exploit when we introduce the following comparison tests is that each of these series kind of is related to, kind of looks like another series that we do know how to deal with. For example, here, 1 over k squared plus k plus 1. When k is large, and we are considering the terms that are off toward positive infinity, this rational expression, 1 over k squared plus k plus 1, the behavior of this expression is completely controlled and dominated by the terms with the highest power. In our case, 1 over k squared. And the sum of 1 over k squared is something that we know about, because that is a p-series. Similarly, for the second expression, when k is large and we're looking off toward the right horizon of this series, the right horizon being the part that determines convergence, this behaves like the ratio of its leading terms, k on the top, 3k squared on the bottom, 3k cubed on the bottom, which is simply 1 over 3 k squared. Just a constant multiple of 1 over k squared, and so once again, p-series would imply that this series on the right side would converge. Because our series is similar to that one, would our original series also converge? And likewise here, when k is large, 1 over k 2 to the k, the behavior of this is dominated by 2 to the k, because 2 to the k is growing so much faster than k is. 2 to the power k is a geometric series. So, because that series converges, 1 over 2 to the k, can we also conclude that our original series converges? And the theorems that we're about to introduce say yes. You can take a series and compare it to another series that behave similarly when k is large. Under the right circumstances, those two series will converge together or they will diverge together. The behavior will be the same. So let's state the first of the two comparison tests. And there is one condition, one important condition that needs to be satisfied before you're able to use this test, so just be careful. You're going to have two series. In general, you're going to have one series called A that you're trying to understand. And you're going to have another series called BK, sum of BK. And this is going to be some other series whose behavior you already understand. By way of some other test. For example, scrolling up to the previous page, the setting would be like, I have the series 1 over k squared plus k plus 1, and I'm trying to figure out what this series is doing. The series that I'm going to use for comparison, the series bk, whose behavior I already understand, would be the sum of 1 over k squared. I already know that that converges via the p-series test. So you have one series that you're trying to understand, and then you have some second series that you're going to compare to the first, some second series whose behavior is already known. Be careful before you use this test and make sure that both the series that you're trying to understand and the other series that you're using for comparison both have only positive terms. If any one of the terms in either sequence is negative, then you can no longer use this test. It's still locked. There are two parts to this test. Scenario 1, suppose that the series that you're using for comparison, the one that you already understand, suppose that you already know that this series diverges. Suppose that you also know that this series is consistently smaller than the series that you are trying to understand. So bk, every single bk, is underneath ak. If that's true, then the series that you're investigating must diverge as well. Now this test also has a second half, and this is the half that you use if the series that you already understand, if that series happens to be convergent instead of divergent. If your comparison series converges, and if the terms of that series are always on top of the terms of the series you're trying to understand, then the series AK has to converge as well. So let's be clear about what this is saying. The divergent series will basically push up a larger series. It will push it up from underneath, forcing the larger series to also diverge. But if you have a convergent series, a convergent series will basically push down any series that's underneath it. This is the theorem that we would want to use if we have a series sum of AK which is smaller than a convergent series or bigger than a divergent series. Let's consider, for example, the series where we're summing up the terms of this k squared plus k plus 1. Now, if I look at the terms of the series, 1 over k squared plus k plus 1 is definitely going to have to be smaller than if we just had 1 over k squared, because we're dividing 1 by a larger quantity. And if you divide by something larger, you're going to get something smaller. Now, we know that the series 1 over k squared converges by the p-series test. Which means that the convergence of this series is going to squash down any smaller series and force the smaller series to converge as well. As a result, our series, being smaller than this one, has to converge too, by direct comparison. Let's have a look at this second example. The sequence that we're summing up for this example is 1 over natural log of k plus 1. Now, in order to get an idea of what I can use for comparison, I've gone over here to Desmos. And I want to have a look at the function natural log of some input, let's just call it x, versus the input x. Notice that the output of natural log is always smaller than x itself. This cyan graph is always underneath the orange graph. So the value of natural log of x is always smaller than the value of x. So let's have a look at natural log of k plus 1. This quantity, the output of natural log, must always be smaller than the actual value that went into the natural log. In our case, k plus 1. So if we reciprocate those quantities, if I take 1 and divide it by the natural log of k plus 1, then that has to be larger than the reciprocal of k plus 1. Now, if we look at the sum of 1 over k plus 1, this is not quite technically a p-series. If we just had 1 over k, that would be a p-series, but we have 1 over k plus 1, so this is no longer a p-series. However, we can use the integral test to determine whether or not this series converges or diverges. Let's integrate from the starting number 1 up to infinity, 1 over x plus 1 dx. This is equal to natural log of x plus 1, evaluated from 1 to infinity, so this diverges. Which means that this original series here, 1 over k plus 1, diverges. Because that series diverges, it's going to cause any larger series to diverge as well. It's going to push up any larger series so that it's also going up toward positive infinity. It's going to push it up from below. So the larger series, the one that we have, 1 over the natural log, must diverge as well. And let's have a look at the following application of the direct comparison test. Spoiler alert, this one is not applied correctly, and let's try and figure out what has gone wrong here. Consider the series n minus 1 divided by n squared. The student looking at this series has the idea to compare it with 1 over n, the harmonic series, because the series that they have been given looks a little bit like n over n squared, which simplifies to 1 over n. Now the student says for every index n, the following inequality is true. The term in my series, n minus 1 over n squared, has got to be less than or equal to n over n squared. Because if you subtract something from the numerator, if your numerator is smaller, then the entire fraction must be smaller. N over n squared is of course equal to 1 over n. So they find that their series is less than or equal to the comparison series that they have chosen. Now the comparison series 1 over n definitely diverges. It's the harmonic series, which is a p-series with p equals 1. So they say, by comparison with the harmonic series, the series that we started with, sorry I wrote the typo, the original series n minus 1 over n squared must also diverge. What do you think? Is this logically valid or invalid? And if it's invalid, where do you think the student went wrong? Harmonic series 1 over n is known to diverge by the p-series test. So it must push up any larger series toward positive infinity, forcing any larger series to diverge as well. However, the series in our problem is not larger than the harmonic series. The series in our problem is smaller than the harmonic series. Because our series is smaller than the harmonic series, direct comparison test is locked. Because the hypotheses of the direct comparison test are not satisfied. What's logically invalid is that the inequality went in the wrong direction for comparison with a harmonic series. So let's go ahead and give the second comparison test for today, which is the so-called limit comparison test. And limit comparison test is personally what I would use if I wanted to construct a formal argument to investigate a series like this one, n minus 1 over n squared. This series does seem conspicuously similar to the harmonic series, because the only difference between our series and 1 over n is this difference of the minus 1 in the numerator. But when n gets really, really large, minus 1 isn't going to be making that much of a difference compared to the terms with a higher degree, n and n squared. And so that is what the following test is all about. It gives us a way to take a series like n minus 1 over n squared and compare it to another series which behaves similarly, even if we can't quite get direct comparison tests to work out because of the direction of the inequality. So here's the setting. We have two series. We have the sum of a sub k and we have the sum of b sub k. And just as in direct comparison test, usually we have some information about one of these series. Maybe this one is understood. And then we have some other series which we are trying to understand by comparing it to a series that we do understand. if both of these series have only positive terms, so no negative terms allowed in either series, and if the limit as k goes to infinity of the ratio of these sequences is a finite non-zero number. If you take the series with the sequence ak and divide that sequence by bk, take the limit as k goes to infinity, and get something which is strictly less than positive infinity and strictly greater than 0, then the two series, the one that you're trying to understand and the one that you already understand, have exactly the same behavior. Either both series diverge or both converge. So this theorem is incredibly powerful because as long as this hypothesis is satisfied, that the limit of the ratio of ak to bk is a finite non-zero number, then you don't have to do all of this fussing around with inequalities. You know immediately that if the comparison series bk converges, then your original series ak must also diverge. And if your comparison series bk diverges, then so must your original series sum of ak. So let's get some practice using this truly wonderful theorem. First of all, let's outline when a theorem like this would be useful. A theorem like this would be useful if you have a sum where the series ak behaves like a well-understood sequence bk as k gets large. And one of the fundamental principles that we will be using when we ask the question, what does this series behave like, is that a polynomial behaves like its leading term, the term with the largest degree, the largest exponent. When k starts to get really, really large, the impact of 3k and the impact of 1 is not very significant compared to the impact of a gargantuan term like k to the 4th power. K to the 4th power, the leading term, is going to be growing so much faster than any of the other terms that that leader is going to eventually dominate the behavior of the entire polynomial. So let's use that principle to check out some of the following examples. Determine whether the series converges or diverges. So the first series that we have has k plus 1 on the top and 3k cubed plus 1 on the bottom. Now, when k starts to get large, this fraction begins to behave like the leading term on the top, k, and the leading term on the bottom, 3k cubed, which simplifies to 1 over 3k squared, which is just a constant multiple, 1/3, times the p-series, 1 over k squared. Now we understand the p-series really well. We have the p-series test that helps us to determine convergence divergence. So I'm going to use for comparison the p-series 1 over k squared. So now let's look at the ratio. Let's look at the ratio of AK to BK. AK is the fraction with k plus 1 over 3k cubed plus 1. And BK is the fraction with 1 over k squared. And if we go ahead and we clean this up, then we get k cubed plus k squared divided by 3k cubed plus 1. Now, as k goes to infinity, this rational function begins to approach the ratio of its leading terms. In our case, k cubed over 3k cubed, which is the number 1/3. Now this number is non-zero, it's larger than 0, but it's also finite. We have satisfied all the hypotheses of this test. Limit comparison test kicks in and tells us that our comparison series and our given series have exactly the same behavior. So because BK converges by p-series test, it must also be true that our original series must have exactly the same behavior. So our original series must converge as well. By the limit comparison test. Now let's consider the following second example, where the terms in the sequence that give us our series have the formula n minus 1 divided by n squared. Now, do you have an idea of what series you might want to use for comparison with this one? Although the harmonic series 1 over n could not be used for a direct comparison because the inequality went the wrong way, that series can be used for limit comparison. Take the leading terms, n on the top, n squared on the bottom, 1 over n. Let's use this harmonic series for comparison with our series. Note, 1 over n diverges by the p-series test. So let's take the ratio of our series to the comparison series. Let's rewrite that as n squared minus n over n squared. As n goes to infinity, this rational function begins to approach the ratio of the leading terms, which simplifies to the number 1. Once again, we have achieved a non-zero finite number for the limit. By limit comparison, the original series must have exactly the same behavior as the harmonic series, which means that the original series in your problem must also diverge. In the next series, we are not given an explicit formula for the sequence, but we have the terms 1, 1 over 3, 1 over 5, 1 over 7, and 1 over 9. So first, let's see if we can find a formula for the terms in our series. Now let's notice the fact that all of these quantities can be expressed as 1 divided by some number. And that number in the denominator is being represented by an arithmetic sequence, which is going from 1 to 3 to 5 to 7 to 9. In other words, it's always increasing by 2 units. That's our common difference. And finally, our initial denominator, the very first one that we were given, was a denominator of 1. All right, can you think of a suitable other series that we can use for comparison with this one? I think that the easiest one is to use the same harmonic series that we used in the previous example. As k gets large, 1 over 2k plus 1 begins to behave like 1 over 2k, the ratio of the leading terms, which can be thought of as 1/2, just a constant multiple of 1 over k. So I would use 1 over k, the harmonic series, for comparison. So if I took a sub k and divided it by b sub k, then that simplifies to k over 2k plus 1, which begins to approach k over 2k. It begins to approach 1/2 as k goes to infinity. So once again, we've achieved a non-zero finite number, and therefore our given series behaves like b sub k and also diverges by limit comparison. Now, although I do love limit comparison tests, and I prefer it greatly to the direct comparison test, there are some occasions where limit comparison is not going to be the test that you want to solve the problem. So for example here, determine whether or not the following series converges, and let's give a formal argument. So someone says, okay, what if I try and compare it with b sub k equals 1 over 2 to the k? I do know, for example, that 2 to the k is going to grow much faster than k will. So maybe it will suffice for me to take 1 over 2 to the k, simply the geometric part. Notice that b sub k is a geometric series with a common ratio of 1/2, so b sub k must be convergent. But if I try and do a limit comparison with my original series, let's see what happens. I take ak divided by bk. So if I take 1 over k 2 to the k and divide it by 1 over 2 to the k, when I simplify this, the result of the simplification is 1 over k, which approaches 0 as k goes to infinity, which means that the limit comparison test is still locked. Limit comparison test required the limit of the ratios to approach a non-zero finite number. But here we have obtained a limit that was equal to 0, so limit comparison test hypotheses have not completely been satisfied. Now, once you encounter a situation like that, there are usually two possibilities. One is to try limit comparison with a different choice for bk. But I'll be honest with you, looking at this original series, I'm not getting particularly inspired for a different bk that would work better in this problem. So let's try and think of not another comparison series, but let's think of maybe another test that might work better for this series. And I think in this case, direct comparison will actually work better than limit comparison. Note that our sequence 1 over k 2 to the k always has to be less than or equal to 1 over 2 to the k, because our denominator is always going to be larger than the comparison sequence 1 over 2 to the k. As a result of that, our series is smaller than a convergent series. So it's being pushed down toward convergence by the larger series. And as a result, we can say, not from the limit comparison test, but from the direct comparison test, that our series must be convergent as well. So, at the bottom of the page, and don't worry, I'm going to post this to Canvas, so you don't have to pause the video and try and copy all this down manually. I have a summary of all the different techniques that we have established so far to determine convergence/divergence of a series. We only have a few more tests left to give, and then we will have a complete list of all the techniques that will be on the table for our class. Of course, there are many more techniques out there in the universe than we would ever possibly have time to cover in a single 11-week course. But we're going to focus on the 9 or 10 tests which are the most broadly applicable to the most common types of series that you might encounter in your physics or engineering courses. The first technique that we had was the original definition of what it meant for a series to converge. So that technique was to find a formula for the nth partial sum and then to take the limit of that formula as n goes to infinity. Now, this is most conducive in a situation where you have a telescoping series, or in more general terms, on any series where S sub n has a really simple formula, something that you can easily simplify and easily take the limit. The next thing that we had for the techniques on our list is, when does a geometric series converge? If you very specifically had a geometric series, you could very easily determine convergence simply by looking at the common ratio. We had the divergence test, a very quick and easy theorem to use, but most of the time the theorem is locked and can't be used at all. Divergence test is only viable when you have a series whose sequence goes to either infinity, or the limit does not exist, or the limit is a non-zero number. If either of those things is true, then you know for sure that your series diverges. Integral test is great if your sequence is something that can be integrated and also represents a continuous positive and decreasing function, which gave us the p-series test, which is of course only applicable to the actual p-series. Finally, we've just introduced direct comparison and limit comparison test. These can only be used on series with positive terms, and they can be only used on series which can be compared to another series that you already understand. And in upcoming days, we'll be dealing with series that might not have entirely positive terms. Maybe some of the terms in the series are negative. And then we'll be trying to deal with series that might have a factorial in them. How do we deal with series like 1 over n factorial? Is a test that's very useful for that situation. To summarize today's material, we introduced 2 types of tests, direct comparison and limit comparison, that could be used to determine convergence/divergence for series that kind of looked like, kind of behaved like, series that we already understood as a result of using one of the other tests. And we talked about some valid and invalid applications of those tests.